So let's get started. The first thing, since we don't have any concept, let me ask you a few questions. You know, the first question relates to one of your homework questions. So there was a homework question which said you have some kind of a sphere with uniform charge everywhere. So this has volume charge, and this is uniformly distributed on this sphere. Okay. Now in the sphere you make a hole. You make some hole. Let's say that this radius of this big sphere is b. I don't know what it was, but let's call it b. The radius of the small sphere is a. And the question was saying, so this is hole now. There's no charge in this region. Okay, and that hole is spherical. Now the question that you were asked was, how will you find the electric field at some point, let's say at a distance little r away, inside this cavity or hole? So how would you find the electric field at this point in this cavity? So when you are asked for electric field, that means you are asked for both magnitude and direction. This was one of your homework questions. Now if you remember from class, we did already talk about how to find the electric field due to a uniform sphere of charge. Remember? Due to a volume charge, we already found the electric field. So if suppose this hole was not there, without the hole or cavity, we already learned this, that if you look at the electric field as a function of r, it increases linearly and then it falls off as 1 over r square. This is your r is equal to b. R is equal to the radius of that hole, of this big sphere. Do you remember that? That initially E is proportional to R. By the way, is everybody familiar with this symbol here? Proportional to? This symbol here is read as proportional to. So that means electric field goes as R. There is some constant there. Okay? And then here electric field is proportional to 1 over r square. Just like E is equal to kq over r square. This is something that we already worked through. I want everybody to take 1 minute, not more than 1 minute, to talk to a person next to them and tell me, you know that this is the electric field. You know, we worked out this in great detail. Remember we said how we worked it out? We said, you know, charge density was given, that was rho, which was equal to the q, which is total charge, divided by 4 over 3 times pi times b cubed. B is the radius of this big thing. And then this should also be equal to q enclosed divided by 4 over 3 pi r cubed. Because basically when we worked through this and when we were trying, so I'm now talking about without the hole. I'm just talking about electric field due to this case. I don't want to confuse you. I'm talking about the case that we already discussed in the class, which was like this. Okay, and for that we found this, because what we had found really was this. We found for this case that you can write the electric field like this. You can show that the magnitude of electric field is really going to be k, q enclosed, divided by r square using Gauss's law. And remember what Gauss's law was. Gauss's law said that the flux through any closed surface should be equal to charge enclosed divided by epsilon 0. And how did we actually do this? We basically said, well, if you ask me to find the electric field, this is without a hole. And what we said, if you ask me for electric field at a distance r away inside, I'm going to draw a Gaussian surface here, which is a concentric sphere. And then since the electric field magnitude at every point on this thing is constant, I can pull the magnitude of electric field out, right? Because this E dot dA really means magnitude of A, magnitude of dA times cosine theta, where theta is the angle between the electric field and the area vector, right? And what we said is that in this case, you can show for sure that this, you can be sure that this gets pulled out. Cosine theta will be cosine 0, which is 1. Integral dA is the total area, which is 4 pi r square. As soon as you do this, you will get this. K is 1 over 4 pi epsilon 0. Okay? But the question was, how do you find Q enclosed? And we said we can find the Q enclosed if only this much charge is enclosed out of a total charge Q, which includes everything, by using this. We can make use of the fact that total charge divided by the total volume of this whole sphere should be equal to the charge that is enclosed inside our Gaussian sphere, imaginary sphere, divided by the volume of our Gaussian sphere with the little radius. And using this relation, you can write what is Q enclosed in terms of the total charge. Do you see this here? That from here you get, in fact, it's obvious now that Q enclosed turns out to be, look from here, it turns out to be Q times 4 over 3 pi r cubed divided by 4 over 3 pi r cubed. These things get cancelled. So that means Q enclosed is equal to Q r cubed over r cubed. And if as soon as you plug this here, do you immediately see that r cubed, there is an r cubed and there's an r square, 2 of the powers get cancelled, you get E proportional to r. Why? Because all the other junk, capital Q, R, K, etc. is constant. Those things don't change. What is variable here is little r. Okay? And that's how we have gotten this. So I want everybody to think about now how you will do your homework problem. And I know that people who have already done this homework problem probably will take less than a minute, but I want to give you 1 minute to think about how will I solve the problem in which the problem has now been complicated by the fact that not only is it just a volume of charge uniformly distributed on a sphere, but there is a cavity from which the charge has been taken away. Talk to a person next to you, please. How would you solve that? Knowing the answer to the uniform sphere.
Because that would be
all right, anybody has any thoughts on how to approach this problem? This is your homework problem, problem 77 from the textbook. This is the homework that is due this week. Anybody? Any thoughts? Go ahead. This was your homework problem. It doesn't have to be right. You're just learning the material, but let me hear some of your thoughts. How would you do it? I already reminded you how you would do it if there was no hole in it. You would do it like this, right? You would find Q enclosed, you'll do it this way. How would you do it now with a hole? Any thoughts? Go ahead, please.
Do you need to draw your Gaussian surface first?
Yeah, you can use the same kind of thing that we are talking about right now. Can you think of using the superposition principle in a clever way? One clever way would be, I can think of this situation like this. I can think of it as being a full sphere like this. Something whose answer I already know. This, right? Minus what? I want to write it as something minus something such that I know I can apply this idea to each of those cases. What do I have to subtract to get the sphere with a hole? Go ahead.
The charge the sphere of the hole has charge.
Yeah, very nice. So the thing is, basically I can actually think in my mind, okay, let me keep the whole sphere. If I subtract from it the electric field due to just this, suppose there was some charge in the sphere. If I subtract this thing from this, isn't this equal to this thing with the hole? You see what I'm saying? Now we do have this hole or cavity. But we are saying, oh, hole with a cavity is equal to having the full sphere minus the charge in the sphere. Isn't that true? Do we know how to do this? So now you are asked, okay, find the electric field at some point. Let's say at a distance r away from its center. Right? The radius of this is b, let's say. The radius of this hole. Now the hole, you're imagining in your head, what if the hole had charge? With this, sorry, this is A. Right? So do we know how to find the electric field due to this? Or not? Yeah, this is exactly this. Right? And do we know the direction of the electric field at this point? Which way will the electric field be? Remember? Yeah, it's always radially outward for uniform charge distributed on a sphere. So we know that the electric field due to the whole sphere, right, is going to be radially out like this. Right? Okay, now what about, let's say that this point here for just this thing is somewhere over here. Okay? So if that point is somewhere over here, this I'm talking about the same exact point now from the perspective of just the little sphere. And let's say that point was over there. This is where we are trying to find the electric field. What is the direction of electric field? You know, and let's give this length some name. Let's call this thing, let's say r prime. So which way? This is r prime. This is vector r. Now the question is, which way will be the electric field due to this little sphere that we want to subtract off? Is it again going to be radial since it's uniformly distributed? Yeah. So again we'll say, oh, the electric field is radial along this direction. Now what we have to do is subtract the two electric fields. Right? And do we know the magnitude? Yeah, we very much know the magnitude. It's this. The magnitude actually is exactly this. So this is going to be, you can either write it in terms of Q, or another way to write this will be in terms of rho. Do you see another way to write this in terms of rho also? Because depending upon what you have been given in the problem, so read the problem. Sometimes the problem will say the total charge is capital Q. Sometimes the problem will say the charge density is rho. Find the answer in terms of rho. I believe in your homework problem 77, it says find the answer in terms of rho. Can we find Q enclosed in terms of rho? Looking at this? Yeah, it's very easy because all you have to say is rho is equal to 4 over 3, sorry, Q enclosed divided by 4 over 3 pi r cubed, right? And that means Q enclosed is equal to rho times 4 over 3 pi r cubed. So either you can put Q enclosed is equal to this or this, depending upon whether you were told to find the answer in terms of the total charge Q or rho. In your homework problem it's saying find it in terms of rho. So let's plug rho here and we can write it as rho. Q enclosed is rho 4 over 3 pi r cubed divided by r square. You can see two factors of r get cancelled and this is k rho 4 over 3 pi times r. Do you see this is all constant? And this is what I was saying, that the electric field is actually proportional to r, right? E is proportional to r and it's radial. Is that making sense, folks? So who wants to tell me, here we are saying that the magnitude of electric field at this point, right now we are finding with respect to not this little thing, but with respect to the whole charge here. Because first we'll find it due to all the charge as though there was no cavity, and then we will subtract from it. So we'll find it as though there was no cavity here, and then we'll subtract from it the case where we are getting rid of the charge in the cavity. Do you see what I'm saying? So who wants to tell me what would be the magnitude? Let's say that the charge density obviously is rho here and it's rho there, right? All I've done is initially I'm thinking of the whole thing, and then I've taken something and removed this part, and so I'm getting rid of the electric field due to that. This is just superposition principle. You can always subtract off or add electric field contributions due to different charges, right? Is this making sense? So who wants to tell me what would be the magnitude of electric field due to this big sphere? Notice you can even make it a little bit simpler. Remember what K was? K was 1 over 4 pi epsilon 0. So you have rho 4 over 3 pi r. What you will see is that all of this gets cancelled, and this is just rho over epsilon 0 r. This is the electric field magnitude due to a uniform sphere of charge. Electric field magnitude inside a uniform sphere of charge at a distance r away, right? Is that making sense? So who wants to tell me what it should be for this point, which is at a distance r away from the center of the sphere? Go ahead, please.
Isn't it E equals P over 3 epsilon 0?
Thank you very much. Absolutely. Very nice. Thanks. Okay, anybody wants to tell me, so what should it be here? What is the magnitude of electric field here? That, right? So it is E is equal to rho over 3 epsilon 0 times r, and it's in this r hat direction. Is everybody seeing that it's in the r hat direction? Let's call this direction r hat direction. Are you guys familiar with the unit vector? Unit vector r hat is just a unit vector that tells you you're talking about this direction, radial direction. Okay, so I'm just going to call it r hat direction. Okay, what would be this is the electric field due to this case. Now I have to subtract off the electric field due to this case. What is the magnitude of electric field at this point if this distance is r prime? Can we again use the same exact result here for the little one? Tell me what it will be for the little one then. The magnitude of electric field, let's give it a name. Let's call it E1. Or we can give it a better name. We can say E full. Full means everything included, assuming that there is no cavity, right? So this is for no cavity. And this is E cavity. That means electric field only due to the charge in the cavity. What will it be? See, I'm saying that same point, this point, if you think from the perspective of this cavity here, I'm saying to you that from the center of this cavity, which has a radius a, this distance is r prime. That's what I wrote. Right? So who wants to tell me what would be the electric field just due to the charge in the cavity? Anybody? Go ahead, please. Very nice. It should be rho 3 epsilon 0 r prime, and this time it's in the r prime hat direction, right? Very nice. This is the r prime hat direction. It's the same exact result. You're just applying it twice. Once assuming that the whole cavity has charge. Another time assuming I'm going to subtract off the charge in the cavity. So this time you're just considering the cavity. Same formula applied twice. Now what do I have to do? I have to subtract these two electric fields. So this is one electric field, this is another electric field. I have to subtract them off, right? So let's subtract the two. So E net then will be E full minus E cavity, and this will be equal to rho over 3 epsilon 0 r in the r hat direction minus rho over 3 epsilon 0 r prime in the r prime hat direction. By the way, another way to write r in the r hat direction is like this. You can also write it like this, right? A simpler way to write this would be 3 over rho over 3 epsilon 0 r minus rho over 3 epsilon 0 r prime, where I'm thinking of these as vectors. Is that making sense to everybody? Okay, so now does anybody know what this vector is? First of all, we can pull out all this junk, the constant, and this is just rho over 3 epsilon 0. What is r minus r prime? I want everybody to talk to a person next to them. You have 1 minute to think about, can I write r minus r prime in terms of the things that I have been given in this problem? I have been told that here are the things you have been told. B is the radius of the big sphere and A is the radius of the cavity that you have dug out, and you're finding the electric field at some point over here in the cavity, right? Do you remember the problem from your homework? And this is what we are calling vector r. This is what we are calling the vector r prime. Everybody should be talking to a person next to them, please. Go ahead. It doesn't have to be in terms of A and B, but the thing is, the question is, what is the physical thing of interest here? It doesn't have to, your answer doesn't have to be in terms of A and B. If you can physically say what is r minus r prime, that would be good enough. So if you can say this is this distance, because it's some distance which is very well defined. This problem happens to be a really interesting problem because the answer is extremely surprising. You won't expect this answer to be the answer. So anybody wants to tell me what is r minus r prime? Not in terms of A or B, just tell me what is that distance and what is that vector. Can you tell me at least in the magnitude of r minus r prime? Please.
Is it the distance from the center of the big sphere to the center of the little?
Excellent. It is nothing, you're subtracting two vectors, and if you form a triangle, you can already see, if you think of some vector like this, right? Do you see that, let's call it vector A, okay? From this triangle, the fact that vector r is this way, vector r prime is this way, and this is vector A, do you see from the rule of triangle, adding vectors here, A is equal to what? Is it r minus r prime from this triangle? Is everybody seeing that? That A plus r prime, look at the way these things are head to tail. So A plus r prime is equal to r. In other words, A is equal to r minus r prime. And so r minus r prime is nothing but the vector that is pointing from center of one sphere to the center of the cavity. Do you see what I'm saying? So this is rho over 3 epsilon 0 times the vector A. And what is so interesting about this result? Is it a result that you were not necessarily expecting? What is so special about it? Because I want everybody to be thinking. If you are not thinking, you will feel that you haven't learned much, because the thing is you have to be thinking right now. Tell me why did I say that this answer is not is very interesting and fascinating? Many papers have been written about how interesting this answer is. What is so interesting about this answer? Go ahead.
It's constant.
It's constant in the sense it doesn't depend upon anything else. Suppose I change the point and I said, I want you to choose the point in the cavity to be here, right? So then your vector r will become this, right? Vector r prime will become this, and hey, the resultant stays the same. If I tell you, no, I don't want you to find the electric field in the cavity over there, I want you to find the electric field in the cavity over here. Same story again. This time your r will be this way, your r prime will be this way, and hey, your a is again the same. So you said something that is absolutely correct. The electric field in the cavity is constant everywhere. If you dig out a hole in a cavity which had a uniform charge distributed on it. So that is a fascinating result, that it doesn't matter where you are in the cavity, the electric field is exactly the same, both in magnitude and directions. This electric field is absolutely the same, whether you ask me, oh, tell me the electric field here or here or here or here, anywhere in the cavity, it's the same. That's a very interesting result. What is this electric field due to? This electric field is due to all of this charge here. Right? Any questions, folks? Anybody? All right, I have one more question before we move on. So this question is about this situation. So suppose you have a cylinder. There's no charge inside the cylinder. But this cylinder is in a uniform electric field. So these are electric field lines. Electric field is constant and it is 2 Newton per Coulomb. Okay? Let me also give you something. Let's say that the area of cross section of this thing, each of these faces here is 2 meters square. The question is, how much is the flux through this surface? Is everybody understanding what the question is? Suppose this was your exam question. How would you do this? I think that's the best way to think about it, because your exam is literally in 10 days or 9 days. Suppose this was a question I gave you in the exam. I gave you a cylinder. I said there's no charge inside. There's some uniform electric field which is 2 Newton per Coulomb, and let's call it x direction. So this is in the x hat direction. The question is, how much is the total flux? Okay, this is the flux. And remember, flux can be written like this, integral E dot dA. So how much is the total flux through the whole cylinder? Everybody should be talking to a person next to them. 1 minute to talk. All right, somebody from the front row. Anybody from the front row, please. Any thoughts? Go ahead, folks. I mean, making a mistake is not it's not a problem at all, because remember, you're just learning. Go ahead. Okay, that would be a good thought. Any other thoughts? Go ahead.
I think it's 0 because the lines are coming in this way on one side and going out this way. So the area vectors, the cosines, one's going to be negative, one's going to be positive, and they're going to cancel.
Yeah, actually the correct answer is 0. But I mean, the other answer was good also, because that is a very common, answer that we might actually think of. And the point that she, the reasoning that she gave is absolutely correct. If you think about Gauss's law, what should be the integral E dot dA? What should be the flux? It should be Q enclosed divided by epsilon 0. You know that there is no Q enclosed here. It says there's no charge inside. So whether the field was uniform or not uniform, there shouldn't be any flux through it. And her explanation was really beautiful because what she is saying is, look, if you look at the physical picture, you can see as many field lines are going in as they are coming out. So there's no net field lines going in or out. Isn't that what Gauss's law says? Gauss's law says only when there is Q enclosed will you have a net flux, because net flux is a measure of, is there a net number of field lines going out of a closed surface or going into a closed surface, right? When you're talking about flux through a closed surface. So in this case, you can physically see whatever is going in through one is coming out, and her mathematical explanation is correct too. She's saying, well, if I really wanted to do the math, I can say, well, the third way to describe it, one way to describe it is just to say Q enclosed is 0. From Gauss's law, this is equal to Q enclosed over epsilon 0. It must be 0. That would be one explanation. The second explanation is this physical visualization, whatever number of field lines going in are coming out. If you really were wanting to be sure mathematically, you could do it that way, and you could say, oh, so the electric field is constant. I'm going to pull the electric field out, right? But what I have to realize is that on this cap, the area vector is outward normal like this. On this cap, the area vector is outward normal like this. What is the angle between electric field and area vector on this cap? 0. What is the angle between the electric field and area vector here? This angle is 180, right? What about, is there any flux through the caps or not? Sorry, not caps, I meant the curved part of the cylinder. There isn't. Why is that? Because if you look at any point here, the area vector dA is going to be always perpendicular to the direction of electric field. Do you see what I'm saying? This thing is 90 degrees, and remember, cosine 90 is 0, so there is no net flux. But looking at this, we can say, so the net flux will be, you know, cap 1, which is going to be the magnitude of electric field, magnitude of dA times cosine, here it is 180 degrees, plus the other cap, cap 2, where again the magnitude of electric field everywhere here is constant, so I can pull it out, times dA times cosine 0 degrees. Is everybody seeing here the angle between the area vector and electric field is the same for this cap? So is everybody saying that seeing that this closed surface can be broken into 3 parts, this cap, and the curved part. But curved part I don't have to worry about because I know cosine 90 is 0. So there is no flux through it. Even visually I can see nothing penetrates, no electric field lines penetrate through it, right? So only the caps I need to worry about. And now notice that cosine 180 degrees is -1, cosine 0 is +1. So both of these contributions add up to 0. Right? But so you can see that the flux through this whole thing is 0 because the contributions here and here cancel each other out. Now the good thing about actually thinking about it visually as opposed to mathematically is, what if I change the question on you and in the exam I said the electric field is non-uniform. So a non-uniform electric field is passing through a cylinder. So I said, you know, here is a cylinder, no charge inside, but this is placed in some external electric field, and it turns out that the electric field is stronger here on the top, and then it gets a little weaker as you go down, so the field lines are farther away. Now if I ask you this question, what is the flux through this thing, what would you say? Go ahead, please. It will still be 0. This for the same reason. You know, this is Q enclosed over epsilon 0. Q enclosed is 0, so this is still 0. So this flux, which is integral E dot dA, will definitely be 0 still, because there's no Q enclosed. Whatever field lines go in, go out, right? Doing the math here would be a little bit more difficult because the electric field is not uniform. You can't pull it out. Do you see what I'm saying? In the third case, I could ask you this situation, I could ask you about this situation. I could say, here's a cylinder, no charge inside. You know, the electric field lines actually penetrate it like this at some angle. Maybe it's uniform. What would be the flux through it? What is the flux through this whole cylinder? The answer is again 0. You know, the thing is, if you wanted to do the math here, integral E dot dA, you again would have to start taking contribution from this cap and this cap. There will also be a contribution from the whole curved surface, etc. So that would be much harder. But if you thought about it visually and you said, hey, I see as many field lines that are going in are coming out, there cannot be any net number of field lines in or out. Another way to think about it is to say, hey, Gauss's law tells me that there is a net flux. That means net number of field lines through a closed surface only if there is a net charge enclosed. If there's no net charge enclosed, there cannot be any net flux. Please go ahead.
If we get something like this on the exam, do we have to do any math, or can we just say since
No, if that depends upon, you know, the question. So if the question is just a multiple choice question, for example, you just have to pick the right answer. If the question says explain your reasoning or something because it's some essay type question, then you have to just explain. But even then you don't have to do the math. If you can give a good reason and you can say, hey, look, I know this, just write this. This is a perfectly valid answer. Flux is equal to Q enclosed over epsilon 0. There's no Q enclosed. It has to be 0 regardless of what those external electric field lines are and how they are going in, because whatever goes in must come out. You know, so every line that penetrates in must go out. Is that making sense, folks? Anybody has any questions about this? Okay, then let's move on to new material. These were all review questions. So I would have typically asked them through clickers, but since we don't have clickers today, I just put them up here. So remember last time we had talked about electric field due to an infinite sheet of charge. And in fact, you guys had come up with, so by infinite sheet, I mean the sheet is extremely large compared to the distance where we want to find electric field. So if this is my sheet here, this will be called almost infinite if you are telling me find the electric field somewhere close to here, right? But if you say, oh, find the electric field here, this sheet is obviously not infinite because for some point here, you can see the edges, right? So just like what I was saying, for somebody standing on Earth here, the Earth looks almost infinite. It looks pretty flat here. But if I were an astronaut in outer space, I couldn't think of Earth as a flat sheet, right? It would look in fact like more like a ball. So you have to think about infinite sheet as an approximation, and sheets are infinite. Sheets of charges are infinite only when you're trying to find an electric field at a point close enough so that the edge effects are not important. But in this course, almost always we are going to assume that the sheets are infinite. In fact, in this course I already told you there are 2 chapters which are completely dedicated to dealing with parallel plate capacitors, and in that we are going to always assume that the plates of the capacitors are infinite. Okay, so all of the stuff that we are doing right now will actually hold for that case. So does anybody remember how we can actually choose the Gauss? So this is infinite in this direction, it's infinite this way, it's infinite this way, and it's infinite this way. And somebody is telling us find the electric field, say at some point over here due to charges on the sheet. Who wants to tell me what kind of Gaussian surface we had chosen to find the electric field here? Do you remember we had already done half of this problem last time before leaving last week? Please go ahead.
Cylinder, half on each side.
Very nice. So what we had said is that obviously the Gaussian surface that we should choose should pass through this point, and we said, well, one way to do this will be to choose a cylinder such that this point happens to be on its cap, and this cylinder is half on one side and half on the other side. So you know the other half of the cylinder is over here. Is that ringing a bell? Okay, so we are trying to find electric field due to a sheet of charge. Okay, so now we are trying to use Gauss's law, and remember Gauss's law says this, so we have to obviously make use of this. We have to make use of integral E dot dA is equal to Q enclosed over epsilon 0. Right, this is what we want to use because we don't want to do any complicated integral. Remember, if we use Coulomb's law, which we actually did, if you go back to your notes from chapter 1, you will see that we did this problem first with a disk of charge, where we started breaking up the disk into little rings and rings into little DQs, and then we started saying, oh, if you wanted to find the electric field at some point, what would be the contribution of different things, and then we started adding them vectorially, and we came up with some complicated expression for integral that we needed to look up in some table. That was too complicated. What we will see is that since we have chosen this Gaussian surface easily, the answer will come out very easily without any integrals or anything. First of all, from the symmetry of the situation, if this sheet is infinite in extent on all sides, what should be the direction of electric field at any point? So if this sheet, say, has positive charge on it, right, and this was infinite in extent, right? If I ask you what is the direction of electric field at some point due to it, what would you say? Go ahead, please.
Perpendicular to the cap, so just straight up.
Very good. It will be perpendicular to the sheet. Why is that? Because think about it. You know, if you think about Coulomb's law and think about breaking up the charges on the sheet into little DQs, into little point charges, you can see that you can always think of one charge somewhere over here on the sheet such that there's another charge which is totally, which is symmetrically situated such that suppose you're trying to find the electric field here, then the electric field due to this one and that one will be such that their magnitudes are the same, and when you look at the components along this direction add up and the direction perpendicular to them cancel out. Similarly, you can think about some charge dq here and some point charge dq here such that their contributions at this point where I'm interested will again be such that this component cancels out and this component adds up. Do you see that? Because this is an infinite sheet, there's no end to it. If there's no end to it, you can always think of charges which are symmetrically situated on the two sides, right? Is everybody admiring the symmetry of the situation? Okay, great. So if that's the case, is everybody convinced that the electric field at any point on this side of a positively charged sheet with uniform charge will be perpendicular this way, and on this side again it will be perpendicular this way, coming out of the sheet? Very good. So basically our point is that we already know that the direction of electric field is definitely this way. And we already know, say for example, if you were looking at some point here, then the direction of electric field is definitely that way at every point. Okay, so if we are sure about that, now who wants to tell me what is the angle between the electric field and the area vector on this cap? Look at dA. dA is like this, right? What about the angle between the electric field and area vector here? Go ahead. Very nice. This is 0 also, because the thing is, if you think of dA, dA is perpendicular outward normal. So do you see that the angle between electric field and area vector is 0? Cosine theta is equal to cosine 0 degrees, which is 1. And similarly here, the angle between electric field and area vector is 0. So cosine theta is equal to cosine 0, which is 1. What about the electric field? What about the electric flux through the cap? What is the angle between the electric field and area vector on, not cap, sorry, I meant the curved part of the cylinder. Because if we want to be able to use this, don't we have to break up this cylinder into 3 parts? This cap, and the curved part. Is there any flux through the curved part? No, there is no integral E dot dA through the curved part, because if you think of any point on the curved part, dA will be perpendicular to the direction of electric field. Is everybody seeing that? That this angle will always be 90? Right? Even if you look on this side, even if you look over here, your dA is going to be like this, your electric field is going to be like this. You can see this angle is 90. So cosine 90 will be 0. Remember, this is this. E dA times cosine theta is equal to this. So if I break this thing into 3 parts, this integral is cap 1 plus cap 2 plus curved part of the cylinder. Is everybody seeing, let's say that the area of the cap is A. The magnitude of the area is A. Is everybody seeing there's no contribution from the curved part? If this is cap 1 and this is cap 2 here, the contribution from each curved part must be such that, first of all, is electric field constant everywhere on the curved part? See, if this is an infinite sheet, then yes. If this is an infinite sheet, do you see that at a given distance away, the electric field magnitude better be the same if this is an infinite sheet? So the thing is, electric field magnitude is constant. I pull it out. Cosine theta for each of these caps is cosine 0, which is 1. So all I have is integral over cap 1 of dA plus integral over cap 2 of dA, and this is equal to Q enclosed over epsilon 0. Okay, what is this thing? I've pulled out E. What is integral dA of each cap? Is it the total area of the cap? Isn't it? And let's give it a name A. By the way, should the answer for what the electric field here is at this point or this point or this point, should it depend upon how big of a cylinder I chose versus how big of a cylinder you chose? It shouldn't. So somehow area should drop out anyway, shouldn't it? Let's say that sigma is the charge per unit length. So sigma is, charge per unit area. This is the charge density. Who wants to tell me how much will be the charge enclosed in terms of sigma? Somebody from second last row. How much is the charge enclosed by this cylinder, because we have to figure out what is this Q enclosed. What is Q enclosed in terms of sigma? Notice that why is this cylinder enclosing any charge? Is it enclosing any charge? Look, here is a sheet, right? This is the sheet of charge. Charge is uniformly distributed. I have a cylinder like this which is coming out in both directions this way, right? Is there any charge enclosed? Yeah, there is charge here enclosed. In fact, that is the reason why this flux is not 0. In this case, the reason the flux was 0 was because there was no charge enclosed. Here there is charge enclosed, and in fact the charge enclosed is right here. Can you tell me what is the charge enclosed in terms of sigma? And the area of the caps that we chose? Oh, come on, go ahead folks. Yeah, please.
Sigma times the area of the cap.
Excellent. We know that Q enclosed will be, is everybody seeing what she's saying? So she's saying that Q enclosed must be sigma times the area of the cap, because that's the size of this thing, this region also. Is everybody up on that? Is that making sense? Okay, so if that's the case, then making use of our Gauss's law, we can see that E times A, integral dA is A, integral dA is A, the area of the cap, which is equal to Q enclosed, which we just now found is sigma over A over epsilon 0. A plus A is 2A, which is equal to sigma A over epsilon 0. A and A get cancelled. Magnitude of electric field is sigma over 2 epsilon 0. So this is the electric field due to a uniform sheet of charge which is infinite in extent. Does this ring a bell? Is this exactly what we had gotten in chapter 21 using Coulomb's law? Please check your notes. When we figured out what is the electric field due to a little disk of charge, uniform charge, and then we had done the extension and said, well, what if the radius of the disk went to infinity so that it became an infinite sheet? I can tell you, if you look at your notes, you will find that this is exactly the electric field. And the direction is perpendicular to the sheet, right? By the way, if the charge on the sheet was negative, the electric field will be pointing again perpendicular to the sheet but towards it. Is that making sense? So all of the answers for magnitudes will stay the same. The direction will become inward, perpendicular to the sheet. Any questions about this? Anybody? Okay, so your midterm is going to be up to here. All right? Now I'm still in chapter 23, but now I'm going to start talking about conductor, which will be for your second midterm. All right? So any questions so far? All right, so let's now try to show, remember a long time ago when we were talking about conductors and insulators, and by the way, those things are there for your test. The only thing that is not there for your test is the kinds of things we'll be doing in this chapter, which will be things like what happens, why is the electric field inside a conductor always 0? Why is it, how will the charges distribute on the surface of a conductor, you know, when you put charges on it? Those kinds of things you're going to learn now, because Gauss's law will make our life really simple and we can easily reason about things and figure out why should charges be distributed in a certain way. All right, so let's actually talk about conductors now. But are you sure there's no question at this point? Anybody, please? Okay. Okay. So now we'll talk about electric field inside a conductor. In equilibrium. And you remember the meaning of the word equilibrium from physics 1? Equilibrium means that there is no net force. So the net force is equal to 0. And if the net force is equal to 0, what does it tell you about the acceleration from Newton's second law? Yeah, that means that there is no acceleration of charges as well. You know, this is the acceleration. Because from Newton's second law, the net force should be equal to mass times acceleration. So basically then, what we are talking about when we say charges are at rest in a conductor, we are saying, and conductors are typically metals, right? All metals are conductors. Basically, there are typically free electrons in these conductors, but when there is equilibrium, there is no net force on these free electrons, their acceleration is 0. So, and it turns out that equilibrium is established extremely fast in a conductor. It takes a very short time, you know, before charges move around and equilibrium is established. So here is the thing. Let me ask you a question. The thing is, suppose you have a shot put, you know, which is made of steel or something. So this is a metal, solid metal ball. And suppose I dump some charges at one end. So let's say that this charge here is 2q. I'm just giving it some name, plus 2q. Do you think that that charge plus 2q is going to stay there for a long time? Or will they move around? Will those charges move around? They will move around, because as soon as you dump charges at one corner of this conductor, the free electrons, you know, there are free electrons all over the place in this conductor. You know, there are these free electrons all over the place. And what will they do? Will they feel a force due to the electric field that is produced by these charges? Yes, and they'll start moving around. And in a very short amount of time, equilibrium will be established. And when the equilibrium is established, what are we saying? The free electrons do not feel any net force anymore. If you draw the free body diagram of each of the free electron, the net force on it will become 0. That's what you mean by equilibrium. And I'm saying it takes a very short amount of time for the equilibrium to be established. Here is the thing. I want each of you to talk to the person next to you, whether you know them or not. This is a good time to start talking to them. Here is the question for you. Can you think about what would be the charge distribution on this conductor in equilibrium? You know, because you already have learned enough about a sphere of charge in order to say what would equilibrium mean. What would equilibrium mean? So talk to a person next to you, and the question is, you know, please. Means what I'm saying is that those charges are not going to stay where they are. I put some charge 2q at some corner. Those charges are not going to stay there. They will move around because there are free electrons in this conductor. And the question is, the charges will move around and an equilibrium will be established after some time, which is a very short time. And the question is, so in the end, when the equilibrium is established, what does the charge distribution on this conductor look like? You know, what has happened to that charge 2q? You see what the question is? All right, folks, anybody wants to help me out? Folks, go ahead. This is a friendly class. You're still learning the material. Anybody wants to share their thoughts about what would happen in equilibrium? Go ahead, please. Anybody? Oh, there's nothing wrong in, yeah, please.
Is the charge spread out on the surface?
Uniformly?
Yeah.
Okay, so his thought is that maybe this 2q charge will spread out, and one way the charges will spread out will be that maybe if there are electrons, suppose there's a positive charge and electron, this electron, if it goes and neutralizes something over there, now you're left with positive charge here, right? If suppose, you know, there's some electron here that goes and neutralizes something over here, now you have a positive charge here. Suppose there is an electron with a positive, you know, close to a positive charge here. If this goes and neutralizes, then you have a positive charge here, right? So the thing is, so his notion is that this charge plus 2q will uniformly distribute itself on the outer surface in equilibrium when the equilibrium is established. How many people actually agree with him? Okay, good, that's a good thought, but go ahead. Were you going to say something else also?
No, I was just going to ask if electrons are the only thing that can move in there, because wouldn't the positive charge not be able to?
Yeah, you're absolutely right. So electrons are the ones that do the moving, but the thing is, when electrons move from some place to the other place, right, and neutralize something close to the place where they go, positive charges where they go, then they leave behind a positive charge, right? So it's the same thing, whether electrons do the moving or moving is done by positive charges, the net effect can be the same. Do you see what I'm saying? So for example, as I said to you, if there was an electron close to here and it went close to some positive charge there, now you have positive charge left behind here, right? So by that token, the charges are now distributing themselves on the surface, outer surface of the conductor. Now there is a lot of catch here, because I could ask you, why is it that the charges are actually distributing themselves only on the outer surface of the conductor? Why isn't it, you know, one thing that should come to your mind is, why isn't it that, yeah, it's true that these positive charges repel each other and stuff, but why is it that these positive charges don't uniformly distribute themselves as far away as possible in the whole short put? So for example, in this room, if suppose all of us really hated each other, and we wanted to be really far away from each other, would the best thing to do be to go and get stuck close to the walls and just line up as far away from each other uniformly on the walls? Or would you think that some people should be here also, some people should be there also, etc., right? But that's not what we are talking about here. We are saying, even though these positive charges are all hating each other, they all repel each other, from Coulomb's law we know, somehow none of them stay in the inner core of the short put. They are all distributing themselves uniformly only on the outer surface. Can you think of a reason? Somebody was going to say something about it, why that is the case? Yeah, please.
Well, they're distributed on the surface, that allows them to have the greatest radius, distance away from every other charge. Right?
Actually, that is not true, because the thing is, because that's what I'm saying, that actually if you really think about, just think about it carefully in your mind. Suppose let's think about the case when you only have a few charges, right? Let's say you had 100 charges. The question is it best for the charges to distribute themselves in the area which is 4 pi r square, where r is the radius of the sphere, or should they distribute themselves in a volume which is 4 over 3 pi r cubed? You see, there are these two questions, and they won't necessarily be the farthest when they have to only distribute themselves on the area. Just like this example that I gave of us. If suppose there were 10 people in this room and all 10 of us wanted to be as far away from each other as possible, the best situation will not be just for us to get stuck on the wall, because then some people will be really close to each other. The best situation might be to somehow distribute ourselves somewhere in the volume of this room. You see, everywhere. And the point is that that's not the case here. And go ahead, please.
But isn't there there's no force from outside the ball, so isn't it the other thing from the other side still pushing out towards that way? So there's nothing it's a close thing, there's nothing outside of it.
As opposed to?
If it was just in space, but it's pushing from the other side, it's stuck, it can't move.
Well, it is stuck. There is no doubt that it is stuck. But the thing is, we have not proved right now that there cannot be any positive charges, say, over here, because the point is that if you could have some charges here, that could have reduced the distance between some of these charges over here, which are only on the surface. But the point is that we will prove in a second, in fact, that that cannot be the situation. Why not? In fact, Gauss's law comes to our rescue. We can easily see it using Gauss's law. Here is the thing. Equilibrium, we already said, means this. Equilibrium means no net force. If there is no net force, what about the electric field that is produced by the charges? Should the electric field be 0? If the net force is 0? Shouldn't it? It should be. Because if you think about it, how is the net force related to the electric field? Anybody wants to tell me the relationship between force and electric field? Isn't that the relation between force and electric field? So if we are talking about equilibrium and we are saying that there's no net force, that means the electric field inside the conductor everywhere must be 0, because there are free electrons everywhere in the conductor. And somehow these free electrons are not feeling any net force, which must be due to the fact that the electric field everywhere inside the conductor is 0. And that is the meaning of equilibrium. Equilibrium means there is no net electric field inside the conductor, because otherwise the free electrons that are there will feel a force due to that electric field. So somehow we have to keep the electric field 0. So what I'm saying is F net equal to 0 implies that E is equal to 0. So that means what we are saying is that E is equal to 0 here, 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 everywhere in this conductor, E is equal to 0. There's no place here where electric field cannot be equal to 0. By the way, do you remember that last week when we were talking about how to find the electric field due to a uniform sphere of charge? What did we say about any point what is the electric field at any point inside the sphere due to charges which are uniformly distributed outside? Yeah, go ahead. 0. Do you remember that? Using Gauss's law, we had beautifully proven something that would have been impossible to prove using Coulomb's law when you are taking little dq. If I ask you, oh, what is the electric field here due to charges that are uniformly distributed on the sphere, and if you only knew Coulomb's law, boy, will it be hard to first of all take the vector sum of all the electric field due to the point charges, not only that, it'll be very difficult for you to prove to me that the electric field here, 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 everywhere inside is 0. Something that we were able to do in a very nice way, elegant way, using Gauss's law. We proved there is no way the electric field has to be 0 everywhere inside. Do you remember that? Okay, so that means that in order for the electric field everywhere to be 0, charges in this case on the sphere must be uniformly distributed, right? Because that's what we have already seen. For a uniform sphere of charge, the electric field everywhere inside is 0. Now let's think about what would be the problem. What would be the problem if there was some charge, say for example over here. Suppose there was some charge left inside the bulk of the short put, right? Some charge said, oh no, I really want to, some of this 2q charge decided, oh, one of them wanted to be there. Is there a problem? Yes, you know, one way to see that there is no way that you can make the electric field 0 everywhere here, which it must be in equilibrium. And I told you that free electrons move around extremely fast and equilibrium is established in a very short time, very, very short time. So what would be the problem if there was some positive charge left behind and you know there were no free electrons close to it? The problem would be, think about just drawing a Gaussian sphere in your head. If you use Gauss's law, if we use this, is there a Q enclosed in this hypothetical thing that you're thinking of, hypothetical sphere? Is there a Q enclosed now if there was some charge left over? Yes, and in that case, if this is not 0, if Q enclosed is not 0, do you see that you cannot have the electric field be 0 at every point on that Gaussian sphere? You know, maybe it's 0 at some place, but not everywhere, because what is really adding up to give you Q enclosed divided by epsilon 0? Remember, this is a sum. Integral is a sum. What is adding up is E dot dA. If E was 0, all this point, if you were saying to me, no, electric field can still be 0 all these places somehow, due to all these charges and due to this charge, if that was really true, then Gauss's law is not going to work. And this is a fundamental principle, because now I know for sure that there is a Q enclosed inside this thing that I've chosen, right? Do you see that there is a Q enclosed now? And if there is a Q enclosed, electric field cannot be 0 at every point on this imaginary sphere that I've chosen. There must be some place at least where electric field is not 0. So that means if this cannot be an equilibrium situation. You know, you can make the same argument for anywhere else. You can say, oh, why couldn't there be a charge over there in the bulk? Well, I could think of choosing a Gaussian surface there. Again, the same logic. If there is a Q enclosed, electric field cannot be 0 at every point on this imaginary sphere. That means there will be at least some places where E is not equal to 0, maybe here electric field is not equal to 0, then it is not equilibrium, charges are still moving around. If it's not equilibrium, that means all the free electrons here, they're still feeling a net force, they're still trying to find an equilibrium configuration. Do you see? If you can make the same argument, you know, even if you say, oh no, some of the charges could be really close to the surface here, I can still choose a Gaussian surface here, and I could say to you the same thing. I could say, look, what about the free electrons here on my Gaussian surface? Wouldn't they feel a force due to charge? Because there will be some electric field at least somewhere that is not 0, because there is a Q enclosed. So by this logic, you have ruled out any charges being in the bulk of a conductor. All the charge in equilibrium must be on the outer surface of the conductor. So this is one important conclusion we have reached, that in equilibrium all charges must be in the bulk. Sorry. In equilibrium, none of the charges can be in the bulk. All the charges must be on the outer surface. So no charge can be in the bulk. Okay. Now, what if the conductor was not spherical? What would happen in that situation? So, for example, if you had, say, for example, something that looked like this, and I dumped some charge here. Let's say I dump some charge, which is 5q. The charge can be positive or negative. It doesn't really matter. What will happen? This time, the charges are not going to be uniformly distributed. That means, charge per unit area is not going to be the same here. Charge per unit area close to the pointed edges and less in the more flat places. But what would be the important criteria for what the equilibrium will be when the free electrons don't feel any net force and the electric, what would it be? What would be the equilibrium? How will we determine the equilibrium? What would be the important criteria? If somebody says, again something should happen, so maybe the free electrons should move around and maybe this electron can neutralize this one, maybe there's a free electron here that can go and neutralize this one, maybe there's a free electron here that can go and neutralize this one, etc. But what we will find is that there's more charge density, charge per unit area in the pointy part and less charge per unit area in the less pointy part. And I hope that it's clear to everybody based upon what you have learned here that there cannot be any charge in this conductor in the bulk for sure, right? That reasoning applies to all. But the question is, what is the criteria for equilibrium here? How will the electrons know, yeah, this is a good situation, we have reached equilibrium? That means there is no net force on any electrons, and that would be the case when the electric field at every point inside has become 0. So that is the condition for equilibrium. The condition for equilibrium is that the electric field at every point, so if you look at the electric field at this point due to all these charges, or electric field here due to all of these charges, or at any point inside the conductor due to all of these charges, the electric field will be 0, and that's when the electrons will realize they have reached equilibrium. Right? Is that making sense? That's the criteria for equilibrium. Now, what do you think happens if I let's go back to the problem that we used to talk about a lot, maybe on the first day of class or second day of class. I told you about this. I said, hey, suppose if you have a conductor, right? This is a conductor. What do you think will happen if you bring a point charge close to it, for example, or a comb close to it, a charged comb? What do you remember? Anybody remembers what will happen? Any thoughts, folks? So you have something like this, right? Metal sphere, and you comb your hair. You know that there are now, the comb has become charged. You bring it close to the conductor, not touching it. What do you think will happen? Will there be force on the free electrons in this conductor? Yes, there will be force, but very soon the free electrons will move around in such a way that equilibrium has been established, right? And equilibrium in this case again would mean that the net force on all the free electrons is 0. That means electric field everywhere inside the conductor has become 0, right? And do you remember how the electric field will become 0 everywhere inside? So we are again saying that equilibrium again would mean that the electric field anywhere inside at any point here will be 0. But how will we do that? Right now it's not. Right now it's not 0, it's not 0, it's not 0. In fact, we know electric field due to a point charge is which way? Do you remember it's radially out? Do you see that? That's the way electric, so what will this electric field do to the free electron? Suppose there's some free electron here. Which way will the free electron feel a force? Do you remember F is equal to QE? So first of all, since electron is negatively charged, it's going to feel a force opposite to the direction of electric field, right? So a free electron here will start feeling a force in the opposite direction, a free electron here will start feeling a force in the opposite direction, etc. You can see, and soon free electrons will rearrange. Do you remember what the configuration roughly will look like? Anybody? So this is obviously not non-equilibrium. This is what we should call non-equilibrium. And the question is, what would be the equilibrium configuration? Who wants to tell me what would happen to the charge distribution on this conductor in equilibrium? Anybody? Roughly. Please.
Many of the electrons would begin moving to the left side of the sphere.
Excellent. What will happen is that, again, it's only going to be on the outer surface, right? Because all the charges can only be on the outer surface. Remember the logic that we talked about earlier? That there cannot be any charges in the bulk of the conductor in equilibrium. So all of these charges, what will happen is that there will be some positive charges left behind, because the electrons will run close to the positive charge, and this movement of charges will continue till the electric field becomes zero everywhere inside. Does that make sense? That the free electrons will move around on the surface, and they'll come from this side to this side, and they'll distribute themselves in such a way that if you look at the electric field here, due to all these negative charges, due to all these positive charges, and due to this point charge, all of them add up to give me 0. Similarly, if you look at electric field here, due to these negative, these positives generated, and this point charge, 0. Electric field turns out to be 0 everywhere inside due to the vector sum of all these induced charges and the charge that I have put there. Maybe this is a comb or something on which that charge is. But the point is that the vector sum of all of these, the electric field produced by individual charges, must add up to 0 everywhere inside the conductor, because this conductor is in equilibrium. That's when the free electrons will stop running around and rearranging themselves. Is that making sense, folks? Any questions about this? You know, this brings us to a very important idea. This idea is often called shielding or electrical shielding. Have you heard this word electrical shielding before? What does this word mean? Does anybody know what it means? Electrical shielding? Please.
I've heard of it in like cables.
Sure.
To prevent noise from like being inducted into a cable.
Very good. And you might have also heard that so you can have electrical shielding in cable. Basically what we are saying is that if you have electric field produced by any number of charges, you know, like suppose you have lots of charges here or sources of electric field, do you see that putting a conductor, you know, shields the inside of the conductor from all of those noises? Have you ever been in a metal room? You know, because a lot of scientists, even in our department, a lot of researchers, you know, they have rooms in which they do research which have walls which are made of metal. You know, they're all made of metal cages, all the sides. Why would they do that? Because they don't want any outside charges outside that room to affect their electric field that they are trying to measure in their own experiment. You see? And so what they do when they put a you know, charge out, when they put the metal cage outside, you know, metal wall, what happens to the electric field inside due to any charge outside? Will it be 0? Yeah. You put another whole bunch of charge, you put here minus 3q. Now again there'll be some positive charges induced due to this here, and there'll be some negatives induced due to this here, such that the electric field inside again stays 0. So no matter how much charge you bring outside, the net effect of that will always be 0. In fact, you know, it's interesting because it turns out radio waves, light waves, all these things are electromagnetic waves. So if you go to one of these shielded rooms which have metal walls, and somebody is playing radio outside, and you shut the door, you won't be able to hear the sound because the electric field gets shielded. The outside electric field doesn't penetrate through the wall. Does that make sense? So this is the same idea that actually tells you, have you heard people saying to you that if lightning is striking, it's not a good idea for you to run out in the wild open area. Rather sit in your car. You're safer in your car. Why is that? Because oftentimes the body of the car is made with metal, and again it's shielding the outside electric field. So suppose lightning, actually there is a some lightning striking say 30 or 40 feet away, right? Then the electric field, due to all the charges that are being dumped from the clouds to the ground, that electric field will induce some charges on the body of your car. Think of this as the body of your car, and there are all these charges being dumped. So think of by the way, does everybody know what lightning is? When does lightning strike? Well, it turns out that lightning strikes when charges that have a lot of, when clouds that have a lot of charges, the electric field due to these clouds becomes so large that there is what is called electrical breakdown. Okay, so the thing is, clouds, it turns out, have a lot of charges, let's say negative charge, and that charge will produce electric field, right? And the point is that if the electric field, if E becomes greater in magnitude compared to 3 times 10 to the power 6 Newton per Coulomb, what happens is that air, which is typically what? Air is typically an insulator or a conductor? Insulator. Air is typically an insulator, right? But it consists of nitrogen and oxygen molecules, and it's typically an insulator. But hey, you know what can happen when the electric field becomes greater than this? The air can actually ionize. The air can start acting like a conductor. So basically the positive and negative charges can separate out, and the free electrons in these things, in these molecules, can start moving around. And then the air starts acting like a wire. So you have the air will start acting like a wire, and these charges get dumped to the ground from these clouds, and that's what lightning is. So and this happens when there's electrical breakdown. And that means the air starts acting like a conductor. So the air starts behaving like a wire, and it dumps the charges. So right, so electrical breakdown, and the air starts behaving like a conductor, and it dumps the charges on the ground. So what I was saying is that suppose you are sitting in the car here, and these charges here, negative charges, are being dumped to the ground. What will happen to your car? You will have positive charges induced on one side, negative charges induced on the other side, such that the electric field inside the car stays zero everywhere, right? And that's why you could still be smiling here, while the electric field could become extremely large because a very large amount of charges are being dumped on the ground, right? So again, this phenomenon of electrical shielding is the one that is useful in this situation, that tells you sit in your car, don't start running out. Any questions about this, folks? Okay, so then what do you think will happen in this situation? Let me ask you another question. Suppose now we have two things. So suppose I ask you a question that says, okay, you have some charge, let's say over here, all right? In addition to this, you are also putting charge minus 3q on this, and suppose I tell you, draw an approximate or rough equilibrium situation, equilibrium charge distribution. Okay, I am not going to do it for you. I want all of you to talk to a person next to you. You can see, by the way, this is a point charge. This is a point charge outside. So this is a conductor. What I want you to remember is what will happen to this charge minus 3q where equilibrium is established. What will this charge plus q, which is outside, think of it like a comb, what will that do? Will it induce some charges on this? And if so, you can again use superposition principle. Remember, you don't have to do 5 things at the same time. Think about the case when you only have this. Think about the case when you only have this and add the 2 up. Does that make sense? So what this situation is exactly the same as a situation in which you have minus 3q with no charge plus q. Add to it just this charge plus q. Right? And what you come up with will be the equilibrium configuration of this thing. Everybody should be talking to a person next to them, because tell me roughly what should happen.
Yeah, they should be measured.
All right, somebody from the third row, please tell me what will happen just to this charge minus 3q. In equilibrium, what happens to the charge minus 3q? Anybody? Third row? Go ahead, were you going to say something? When equilibrium is established, what will happen?
It'll go around the sphere on the outside.
Uniformly? Yeah, it's a uniform, so these electrons will move around and they'll uniformly distribute themselves on the outer surface of this thing. All this charge 3q now is uniformly distributed on the outer surface, right? Because we know that when charges are uniformly distributed on a sphere, the electric field everywhere inside is 0, right? And that's what we want. Okay, good, because that's what equilibrium would be. So that's very nice. Okay, what about this? Anybody? What will that do? Just let's only worry about that, please. What will that do?
It'll attract the negative electrons to that side of the sphere.
Very good. It will actually bring negative induced charges here, because electrons like to be close to positive charges, and positive charges will be left behind on this side. And when will this charge separation stop? When the electric field everywhere inside has become 0. Exactly. So if you think about the net electric field everywhere inside this conductor, it will be 0 due to this charge plus q due to all these induced charges, all 3 things taken together, right? All we have to do now is to look at the vector sum of these things. And so basically then what will happen is that now, because of the fact that there is positive here and negative here, right, but this is 3q, so there'll be maybe some negative still there, but much weaker than what was here. Do you see what I'm saying? I'm trying to add up the charges that were due to this plus q that were induced here, and I'm saying if you add these plus q's to this minuses, some of them will cancel out locally, because we don't show the positives and negatives that have cancelled out. The only things that we show in our pictures is the net charge that is left. So is everybody convinced that if there were more negative charges here, I should be showing much lesser number here, because these positives cancel some of these negatives. On this side, on the other hand, if I were showing a certain number of negative, these negatives reinforce them, and we have more negative, right? So these negatives are more in number than these ones, right? Because we have to add this effect with this effect. So it will look something like this. And what will be the electric field everywhere inside? At every place. Okay, now I have a question for you. So I am a scientist doing an experiment inside this metal room. This room is, has metal walls in it. if I have a charge inside, will that charge inside the cavity produce an electric field here in this cavity? Yes, that will of course produce an electric field. When we are using the word shielding, we are talking about shielding the inside of a conductor from outside charges. So any outside charges, spurious noise will not affect anything inside. But yeah, if I have a charge inside, I'm a scientist doing an experiment and my charges will produce an electric field inside. So if I ask you a question like this and I say, oh, this is a cavity, right? And in this cavity, now I am going to put a charge here, plus Q. And this is a metal wall. Will this charge, okay, and let's give us some certain thickness to this cavity wall. So here are two surfaces. This part is metal. The question is, what will this charge inside the cavity do to the inner and outer surface of this metal? Is the question making sense to you? So for example, this is an experiment that you will do in the exploration center. I gave you the exploration problem. So this is like a cavity, okay? And even though it's very tall, so you don't have to worry about the leaking of electric field from the top. So if you put the charges inside, they're pretty well shielded. The question is, if I put a charged thing inside, one thing we are saying, if we have some charged thing outside, let's say this pen had some charges, if I put it here, if this pen had positive charges, I'm going to induce negatives here and positives here, such that the net electric field becomes 0 here, right? What do you think will happen if I actually put a charged thing, let's say this is a point charge, this has some point charge on it, inside the cavity here? What will happen to the inner surface? By inner surface I mean this inner surface here, and what will happen to the outer surface? Because you can see that every conductor will have some thickness to it, right? And that is why I have drawn two surfaces here, one is the inner and one is the outer. Notice that when equilibrium is established, will the electric field everywhere inside the conductor still be 0? And by this inside the conductor, we are just talking about this region here, equal to 0, equal to 0, equal to 0, equal to 0, etc. Right? So tell me, how will equilibrium be established? What should happen? How can the electric field be 0? I mean, is this an equilibrium situation where I'm showing you no induced charges on the inner or outer surface of the conductor? With just this point charge, wouldn't there be an electric field penetrating all over the place through this conductor? That is a non-equilibrium situation, isn't it? So then what should happen? You see what I'm saying? So so right now actually electric field is not 0. If you don't show me any induced charges, then the electric field inside the conductor is not 0, because I can see this positive charge has its electric field pointing straight out, and that's the only charge. But will that actually produce? Notice that this is a hole, this is a cavity. The only place where there's metal and free electron is this region. Okay? The question is, will the free electrons in this region feel a force opposite to the direction of electric field? Remember, F was equal to QE, and free electrons feel a force opposite to the direction of electric field, right? So what do you think will happen in equilibrium? Anybody, folks? Go ahead, please.
The electrons in the metal move closer.
So electron in the metal will do what?
The electrons will move closer to the
Right, so what you're saying is that, okay, so here's my charge in the cavity. This is the charge that I'm working with as a scientist inside this cavity. And you are saying because of this positive charge and its electric field going out, the electrons in this metal here in this region feel a force, and negative charges accumulate here, right? Where did those negative charges come from? From the outer surface. And so now on the outer surface you have left behind an equal amount of positive charge. When do you think equilibrium will be established? Because equilibrium would mean that the net electric field everywhere here must become 0, right? First of all, if these charges are uniformly distributed on the outer surface of the conductor, will they produce any electric field inside anywhere? From Gauss's law, remember? All the charges on the outer surface of the conductor which are uniformly distributed, if it's a spherical conductor, never produce an electric field inside. So the thing is, the only electric field that is produced, say for example, if I'm asking you, tell me what is the electric field at a distance r, and it better be 0, because this is a conductor, and in equilibrium it better be 0, because otherwise the free electrons in these regions will start feeling a force. The only way that electric field can be 0 is if the electric field due to all these negative charges and due to this positive charge cancel each other out. Now do you remember, if this positive charge is at the center of the cavity, do you remember that these negative charges which are uniformly distributed here will act as point charge which is located at the center here for a point if you're trying to find the electric field outside? So that means you have a plus q charge, and then how much should be the negative charge? Should it be minus q? Yeah, so it should be minus q here and plus q here. So you have a minus q charge that produces an electric field at this point, which is as though this minus q charge was at the center, right? And the magnitude of electric field at this point due to the minus q charge will be kq over r square. Due to the positive point charge that is sitting there anyway, because you're doing an experiment with this positive charge, it's kq over r square anyway. The directions are opposite. One of them is radially out, one of them is radially in, because one of them is due to positive charge, one of them is due to negative charge, and so the net electric field is 0. Remember, the charges on the outer surface will not produce any electric field. Does that make sense, folks? All right, have a great day. I'll see you guys on Thursday.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.